WTS reuse is still going on, but research, regulations, and reports now privilege the reuse of wastewater and sewage sludge, biosolids, because they are much more voluminous and with a wider range of applications. However, developing countries need information on the performance of these ongoing practical applications. And developing countries need research on WTS under their specific conditions. And finally, to bring this into reality. Here are some examples of research on reuse for geotechnical applications. There are some key issues. Water content. The wet material is very difficult to work with and very difficult to dry. WTS varies among different water treatment plants and also in the same water treatment plant a long time during the year. The factors that influence WTS composition there are many factors, but the most influential are water source, water quality, treatment process, and dewatering process. The specific application is also an issue because there are different requirements for different applications. The requirements, for instance, for building a dam is different from filling a trench or using the material as pavement base, for instance. As for environmental impact, according to the literature, most WTS are non-hazardous. However, this must always be verified, case by case. The sludges we studied were non-hazardous, but also non-inert. But we think we should test WTS under the application conditions, simulating field conditions. Also, new pollutants must be added, must be screened in the case of WTS because of the discharge of sludge and industrial effluents in superficial waters. So there are some pollutants that should be added to this list of the leaching and solubilization tests. Our research, what we want to bring here, we wanted to investigate the feasibility of employing WTS as collected water content. We know the advantages of drying. Air or oven drying improves the geotechnical properties of soils, but it's time, space, and energy consuming. And we wanted to search solutions for developing countries and small municipalities as well. Also, the multi-purpose application. We thought that investigations directed toward specific use might discard suitable materials for other geotechnical applications. So we tried to screen the overall geotechnical behavior of our materials to think then afterwards about possible applications. Two approaches were pursued. The first approach was the partial substitution of soils with adequate geotechnical properties, so good soils for geotechnics, by WTS to preserve natural resources, that is, to preserve soils. WTS addition decreases the shear strength, increases compressibility, and may also impair the workability of soils. So we searched for the maximum allowed content of WTS that could be added to these soils so they would maintain their good geotechnical properties. The second approach was to mix WTS with additives to design a new geomaterial. So we searched for mixtures that would present a minimum undrained shear strength based on workability and spreading in the field, that is, a workable material for applications involving low soliciting stresses. In the future, we want to go deeper in chemistry and try to design a new geomaterial for multipurpose applications. But for now, we are searching for low soliciting stresses. So we use two WTS from two water treatment plants that use conventional treatment from São Paulo state, Brazil. They are very big WTPs. Cubatão WTP collects raw water from the Cubatão River and supplies 4.5 cubic meters per second to a 1 million population. And Itaiaçupeba collects raw water from a reservoir and produces 15 cubic meters per second of potable water for the São Paulo metropolitan region, which has 21 million inhabitants. And the samples of both WTS were collected directly after centrifuge dewatering. We selected 2 tropical soils that are largely used in earthworks in our state and also are largely occurring soils, a clay sand from Botucatu city and a clay from Campinas city. And the additives were a high purity calcium hydrated lime and a rock powder from a nice granite quarry. Well, traditional geotechnical materials have variability in the field. It is high time that we geotechnicians should use statistics and probabilities when designing, but that's even more crucial for waste. Therefore, we developed a protocol to obtain representative samples based on the theory of sampling. Here's the mineralogical composition of the used materials. The mineralogical composition of Cubatão sludge is compatible with the gneissic rocks and the residual soils through which the Cubatão River flows. Itaiaçupeba WTS, on the other hand, is composed mostly of amorphous phase. X-ray diffractometry could not identify crystalline phases, and the amorphous phase probably is organic matter and also amorphous iron and aluminum hydroxides from the coagulants and also the polymer. Here we see some images of scanning microscopy, and we see that the solids of Cubatão sludge are minerals, soil minerals, sand, clay minerals, what we're used to see. On the other hand, Itaiaçupeba sludge was totally different from anything I had seen before. It had cracks, clusters, organic structures, amorphous matter. It was really very different, and we really couldn't recognize any mineral in these images. From the chemical parameters, I would just like to highlight the cation exchange capacity and the organic matter content. Itaiaçupeba sludge has a much higher content of organic matter than Cubatão sludge, and that is expected because of the different water sources. However, the cation exchange capacity of Cubatão WTS is much higher than Itaiaçupeba WTS. It has a low content of organic matter, and also the mineralogical composition does not explain this high value. It's likely that the method used to determine the CAC, based on exchangeable bases, interpreted the calcium cations of lime addition to the sludge as adsorbed cations. Lime is added for pH correction and also for coagulation, and probably these calcium cations were computed as exchangeable cations and yielded this high value. The same occurred with lime. Lime is composed of Ca, of calcium, so this value has no meaning as a cation exchange capacity. Instead of showing you the water retention curves and porosimetry distributions that we tested for all soils and mixtures, I thought it more illustrative to show a simple experiment of air drying inside the laboratory at ambient temperature to make my point. It took 20 days for Cubatão River, to Cubatão WTS, to reach the residual water content of 14%, as you see here. And for Tayasupeba, it was more than 40 days to reach the residual water content of 30%. So just imagine that in a big water treatment plant, this means a large space necessary for the drying operation. Well, here's some images after the washing of bases and filters, after centrifuge dewatering, and dried till the hygroscopic water content. In this case, dried till the hygroscopic water content, WTS becomes a resistant aggregate with good potential use for geotechnics. Now, the comparison of grain size distribution of Cubatão sludge with and without dispersing agents shows how fluctuated the material is. The grading curve of Tayasupeba sludge could not be determined by sedimentation, even with different dispersing agents that we found in the literature. In all cases, much foam was produced and it was impossible to measure the hydrometer. It's interesting to see that the grading curves of both materials obtained by laser analysis were very similar, despite their being so different. The mixtures were prepared with sludge as collected water content after centrifuge dewatering, and soils at the hygroscopic water content, because soils were air dried. It's a usual practice in soil mechanics laboratories. The proportions of WTS and soil were selected according to an arbitrary criterion of workability of the resulting mixture. These proportions resulted in very low additions of sludge solids to the soil. As you see, the highest percentage was 14% in this case here. Both sludges fell below the A line in Casagrande's chart, indicating that the solids of the sludges are non-plastic of these particular sludges. Tropical soils usually fall around the A line, so therefore, so did the soil sludge mixtures. In the compaction tests, all mixtures, for all mixtures, the maximum dry unit weight decreased and the optimum water content increased with sludge addition. These are all results. And we could find correlations, good linear correlations between maximum dry unit weight and optimum water content versus sludge content. For some traces, the mixtures were prepared wet of optimum, resulted wet of optimum, and therefore were of limited workability. As you can see here, this mixture, or this here, or here, that over two. However, drying the mixture prior to compaction raises the maximum dry unit weight and decreases the optimum water content. Here, I would just like to remember that decreasing our sludge addition reduces the maximum water content. It means that the mixtures are more porous and have more water, are more humid with sludge addition. But when you dry, for instance, in this case, we had here the compaction curve of the clay sand, and here the compaction curve of clay sand mixed with Tayasupeba thinner sludge in the proportion 3:1. And this was the point to start the compaction curve. If we let the mixture dry and then started the compaction test, we obtained another curve, and drying more, another curve, so that there was a recovery of the soil initial parameters. So the sludge addition reduces the maximum dry unit weight, and drying previous testing increases. What's the, you could find good correlations in these cases also. Here is an example. Here is the dry maximum weight of Botucatu clay sand. Then here are the maximum dry unit weights of the mixtures and the correlations versus desiccation ratio. What's the use of these correlations? I think there are some practical uses. They may indicate the use of mixtures with higher WTS content that once are dried to a certain desiccation ratio may show a good performance in the field comparable with that of soil. And drying the mixture is faster and easier than drying WTS alone. Consolidated and drained triaxial tests with measurement of pore pressure yield these results. They are summarized here in the next slide. We saw that shear strength of each soil and its mixtures could be represented by a single envelope in terms of effective stresses. Here we see Botucatu clay and all BC and BT mixtures, and here Campinas clay and all CC and CT mixtures. The friction angles are high, 37 and 36, and the cohesion low, 11 and 12 kPa. These values were confronted with envelopes of many Brazilian soils used in large dams. These are the dams. They are dams, some are more than 40 or 50 years old and are still functioning very well. And we see that our failure points fell inside the range of these envelopes. These are very promising results when we think about geotechnical applications. However, for the analysis of end of construction stability of embankments, we have to consider the undrained shear strength. We found the specifications in the literature of minimum shear strength for geotechnical applications governed by stability and workability, trafficability in the field. And the values varied from 40 to 60 kPa. So here are all the results from the unconsolidated, from the unconfined compression tests, and also from the triaxial tests. And we see that the undrained shear strength decreases drastically with increase of sludge content in both cases. But most mixtures attend to that limit of undrained shear strength equal or higher than 50 kPa. You see only 3 points that fell below this limit. In terms of compressibility, the mixtures present low to medium compressibility. Here we have the undrained, here we have the compression coefficient. The compression coefficient is the compression index divided by 1 plus the initial void ratio. And we can see that the compression coefficient of BC and BT mixtures is 1.8 to 3 times that of the B soil. And the compression coefficient of CC and CT mixtures is 1.1 to 1.8 times that of Campinas clay. So there was an increase in compressibility. Even so, these values are totally acceptable, are inside the acceptable range for general geotechnical applications. They are still not very compressible. And the same can be said about the expansion index and expansion coefficient. Here are some correlations of virgin compression index, CC, as a function of state variables, liquid limits, and initial void ratio. We performed many hydraulic tests, hydraulic conductivity tests, varying confining pressure, and hydraulic gradient. So we didn't find a value, but a range of values of hydraulic conductivity for our materials. What I would like to show here is that sludge addition decreases the hydraulic conductivity of the soil, in some cases reaching the value 10 to minus 9 meters per second. So these materials could also be used as compacted clay liners or other impermeabilization applications or functions. Now I would like to go to the second approach, WTS mixed with additives, lime and rock powder. And we use the same criterion for the mixtures, for the proportions, to find a workable mixture after joining the materials. And here we arrived at dry contents of 5.9 to 28.6% of solids of the sludge added to the materials. The maximum dry unit weight of rock powder sludge mixtures decreases with the sludge content, and the water content, optimum water content, increases. This means that the rock powder sludge mixture becomes more porous and more humid with WTS addition. Lime sludge mixtures present a slight increase in maximum dry unit weight and a slight decrease in water content. So the lime mixtures will become denser and slightly more humid with increase of sludge addition. We performed unconfined compression tests with the as-compacted mixtures, and it was interesting that the stress-strain curves for the lime powder, sludge mixtures increased monotonically with axial strain. So there was no peak in the curves, and we adopted the failure criterion of the stress relative to 15% axial strain. For the rock powder sludge mixtures, there were peaks in the curves, so the failure was very clear. But we can see that the drain shear strength of lime sludge mixtures decreases drastically with WTS content, and WTS rock powder mixtures have lower undrained strength values. I think that that's because rock powder and WTS are non-cohesive, and unconfined compression tests at the end measure the cohesion of the material. Well, really, in the beginning, we carried out some vein tests with the sludge because of the sludge consistency, and also because we wanted to study thixotropy. But soon it became clear that rheometer or flow tests were a better choice. The shear strain rate in flow tests can be varied. This gives more information than the constant shear rate of the vein test. Also, the equipment is much more precise for the low values of shear strength involved. We adopted the plate-plate geometry for the test, also called steel parallel plate. And the sample preparation was that the sludge was mechanically mixed for 1 minute at 2000 RPM before starting the test. Here is the shear rate history for the flow tests we used. You see that there are 2 cycles of shear rate acceleration and deceleration. Shear rate increased from 0 to 50 seconds to -1, which is equivalent to 3000 RPM, and then decreased to 0. Each cycle had 10 steps of acceleration and 10 steps of deceleration, a total of 40 steps, so the test took 400 seconds to be completed. Here are the curves from a flow test following this protocol. And generally, the second cycle alone is used to characterize the rheological behavior of materials, because that is where the steady state of flow is assumed to have been reached. So we should also just analyze these two curves, orange curves here, the second cycle, and here they are. The curves of acceleration and deceleration are different. There is a delay response of shear stress, describing a hysteresis loop. That's the area between acceleration and deceleration curves. Here we can see that for a given shear rate, the shear stress at deceleration is higher than the shear stress for acceleration, and that is called a negative hysteresis loop. And that means that the soil is shear thickening and that there is rheopexy. If we study the very low shear rates, we see that there is an opposite trend. Here we see that for a given shear rate, the acceleration demands a shear stress higher than deceleration. This is a positive hysteresis loop that should indicate shear thinning and thixotropy. And the limit between the two behaviors would be 3 seconds to -1, that correspond to 180 RPM. There is just one problem with stepwise flow tests. They cannot separate perfectly the phenomenon of the influence of shear rate and of time. Rheopexy and thixotropy are related to time, and shear thickening and shear thinning are related to shear rate. And here it's difficult to separate. So we decided to use the first cycle to really understand better what was happening. And here in the first cycle, we see that there was a rapid increase, a peak in the beginning of the test, and then an abrupt decrease of shear stress. So the time between mixing the sludge at 10,000 RPM and starting the test is almost immediately, the sludge agglomerated again. This is a clear indication of thixotropy, confirming what we saw in the hysteresis loop. But here we are certain, we're sure that there was this behavior of agglomeration. And then the stress falls and the viscosity decreases significantly. So we found that we have two realms. The Cubatão WTS presents shear thinning and thixotropy behavior for shear rates lower than 100 RPM. So viscosity decreases, and for higher shear rates, we have rheopexy and shear thickening behavior, and viscosity increases. Viscosity can be calculated always as the tangent of these curves. Well, some practical conclusions can be drawn from these tests. For instance, that stress 350 PA necessary to start flow. Pumping is more difficult to start than when the sludge is already flowing. So it's better to mix the sludge before pumping. And that can be made with and many equipments. A shallow soil mixer would be very useful. This also gives the idea that instead of washing the bottom of the sedimentation bases, we could mix the sediments and pump them, generating a WTS with lower water content. The second cycle at shear rates lower than 108 RPM, with the decrease of viscosity, indicates that this is a very adequate shear rate to pump, because it will avoid pipe clogging, and also indicates that a concrete mixer could be used to produce the mixtures in the field, because a concrete mixer operates at 30 RPM, so mixing will be easier and demand less energy. But more interesting, more important, is that we could substitute the transportation of WTS by trucks, using instead a sludge pipe pumping WTS. This would avoid high fuel costs, vehicle maintenance, contamination potential, and greenhouse emissions. Here are some flow curves for different materials, a second sample of Cubatão sludge, Campinas clay, lime, and rock powder. The values of shear stress, viscosity, yielding stress for the sludge are much higher than for the other materials, as you can see here in the shear stress axis. Also, we see the all materials are shear thinning. Yeah? The tangent here is becoming smaller with shear rate. The lime and rock powder have coincident acceleration and deceleration rates. There is no hysteresis loop, so there is no influence of time in these materials. The viscosity decreases because of the increase of shear rate, and not because of time. Well, Sugawa presented an interesting discussion about the choice of test method, and concluded that it depends on the objective of the investigation and on the material consistency. When the water content is too high, geotechnical tests cannot be applied. Even vein tests do not have precision for such low yielding stresses. On the other hand, for low water contents, rheometers, strength is too high for rheometers. So we have to combine the two kinds of tests. Finally, here there are some results of lime sludge mixtures. Here the lime was added as powdered, and here as suspension. The tests here were unconfined compression tests, and here rheometer tests. In the first case, the results are as expected. The strength increases with lime content and with time. But in the second case, surprisingly, shear strength decreases with lime addition and with curing time. This seems to indicate that, suggests that those chemical reactions associated with lime stabilization just occur below a certain water content. And also that shear strength in the mixtures we studied at early ages must be just due to the addition of a dry material. That is why we looked for another material, a waste, to be incorporated to WTS with the same drying effect, and that was rock powder. However, as always in research, there are surprises, and there are significant differences regarding compaction parameters and the range shear strength comparing lime sludge mixtures and rock powder sludge mixtures. Finally, I would like to make some general comments. The use of sludge and as a geomaterial is technically acceptable and environmentally safe, but of course it has to be studied case by case. WTS is always different from one WTP to another WTP. Fundamental steps for WTS reuse in geotechnics are characterization, determination of geotechnical properties, and assessment of environmental impacts. For all of these steps, adaptation of equipment and procedures may be necessary, as we saw with sedimentation tests and with strength tests. And a protocol for characterization should be followed for each water treatment sludge and each soil and each additive. That means that each water treatment plant must be treated individually. There is no generalization of the results. But for us, geotechnicians, this is no, it's not an issue. We always study the local soil, the local rocks for any work, any project, any that we do. This should be maintained in the case of WTS. Environmental assessment should be based on the real conditions of applications. Leaching tests are very useful for a first screening, but they may discard some materials that will not be solicited, environmentally solicited so much as the leaching test. So it's interesting to see the real conditions of application. Directives for the approval of beneficial uses of waste are needed to declassify water treatment sludge as waste and reclassify it as a byproduct. It would help accepting of WTS reuse. This is true for any waste. People have, do not like to substitute traditional materials for waste. Sometimes the materials and the waste have the same characteristics. It's really no problem, but we must overcome this reluctance to accept WTS waste reuse, and directives are very necessary for that purpose. Partial substitution of soil of WTS is a major advantage for the preservation of natural resources. So these directives will bring benefits because we need to preserve natural resources, and soils are natural resources to be preserved. But this is even more meaningful for countries that depend on agribusiness like Brazil. WTS mixed with local soil for general earthworks in municipalities avoids transportation over longer distance. So we are thinking about reducing the carbon footprint. For large cities, we could recommend the utilization of a sludge pipe between the large WTPs and the processing centers or destinations. So I would say that that second point, fundamental steps for WTS reuse in geotechnics, I would add another step, and that is the study of reduction of carbon footprint and sustainability. And finally, a database of characteristics of raw water and characteristics of water treatment sludge would be very useful to enhance WTS reuse. I would like to thank my school, my university, the Basic Sanitation Company of São Paulo, and the research funding agencies that helped me develop this research. And I thank you all for your attention. I'm here at your disposal, and also my email if you want to contact me.
Thank you so much, Maria. That was a very detailed technical presentation, very comprehensive, very systematic study on water treatment sludge. So hopefully, people I've learned a lot from your presentation and all the techniques that you have used to investigate the complex behavior of water treatment sludge, could be utilized for, other waste materials that people are working on. So you have not only, looked at the fundamentals of this behavior, this material, but also you suggested the practical solutions on how to address those issues. So very, very nice presentation. I really enjoyed. I really enjoyed, comprehensive way that you investigated, and at the end, coming up with the recommendations is the best part of any investigation. Yeah, I agree with you that we should be utilizing, this water treatment sludge and other waste materials from sustainability point of view to conserve natural resources and other things. So thanks again. So just see, you want to answer some questions posted in the chat box. Can you see the chat box?
Yes, let me see. I've seen some